In this section, we'll start chapter 4, and we're going to take a look today at exponential functions and their applications. To review is how we're going to actually begin with talking a little bit about some exponential functions you've seen before, although it's been a little while, even since we've done this back in chapter P. So the first thing to remember is that when you have negative exponents, it actually moves things from the numerators to denominators and vice versa. So on this first one, we can rewrite this one as 1 over 3 squared. In order to change that exponent to be a positive. And then we could actually simplify it further if we needed to as 1/9. The second one is to remember that the 4 to the 0 is a 1. Anything to the 0 power is 1. A secondary component of this is to recognize that that negative is not raised to the 0 power. So this is because it's actually, think about order of operations, the negative, if you will, and the 4 are multiplied together, but the 4 and the 0 are an exponent, and exponents occur before multiplication. So the natural ordering is sort of like there's an understood parenthesis here. So this would actually be a -1 because 4 to the 0, it kind of looks like 4 degrees, but 4 to the 0 is actually 1. On this one, there's several rules going on. There's more than one way to do this problem. For me, I like to get rid of the negative exponent first. So this says -4. I can make this not be negative by flipping my fraction upside down. So this is 3 over 2 to the 4th, which is the same thing as 3 to the 4th over 2 to the 4th. And 3 to the 4th is 81 over 2 to the 4th, which is 16. All right, so just some rules, some properties to keep in mind as you're working with these. We won't use these substantially, but there are occasions where it's useful to see those pieces of information. A standard exponential function actually has the form f of x equals a to the x, and there are some restrictions on what a can be. A, of course, is a numerical value or a number. It cannot be negative or 0, so a's value is greater than 0. In addition, it can't be the number 1. And if you think about it, that kind of makes sense. Let's talk about the negative part first. If you were to have a negative and you raise it to a power, the power will depend on whether or not you end up getting a positive or negative afterwards. In addition, if you had a 0, I'm sorry, not a 0, but a 1 raised to a power, 1 raised to a power is always 1. That would just give you a horizontal line, and that's not an exponential type of quantity. If you're thinking about domain and range on this, and we'll look at the graphs here in a minute, but you're allowed to put any value you would like into the domain. Any x value is allowed, negatives, positives, zeros. So that's values for x, remember, not a. A has its own restrictions. And then the output, well, on an exponential function, if I've always got a positive base raised to a power, then my solution that I'm coming out of that with that is also a positive value. So I have all the values that are bigger than 0 for my range. And we're going to take a look next at how this plays out on a graph. In particular, there are two different graphs that occur. One is the case where a is greater than 1, and the other case is where a is less than 1, still positive, but less than 1. In both cases, if you were to raise whatever the a value is to the power 0, of course you get a 1. So the reason that matters is because that would then be our y-intercept. Both of our y-intercepts are at the value of 1. And let me just give us an example to work with so that we can actually think about what would happen if we were to plug numbers in. So I'm not just sort of throwing this out there in the middle of no. Let's just use a very simple y equals 2 to the x. If you let your x value be 1, then of course y is equal to 2. And we could plot that. So this is a very specific graph I'm plotting now, but the general shape of it is going to apply no matter what the base is, as long as it's bigger than 1. And if I chose a -1, I would get 1/2 because it'd be 2 to the -1, which is 1/2. And so that would look something like this. Now, we already mentioned that when you're raising 2 to a power, you're always going to get a positive number out of it. So you're restricted to being above the x-axis, but you're getting ever increasingly closer to the x-axis as you go. So this is the general shape that you're also going to get, whether I've got a 2 or a 52. It's going to look something like this. Notice on this one, we do have a horizontal asymptote. It's actually at the x-axis, or y equals 0. And the y-intercept, no matter what x value or base value a that we had chosen, is always going to have the value 0, 1 for your y-intercept. Now let's do the same thing on the second one, but let's create an equation where the value is between, the base value is between 0 and 1. So like maybe we have 1/2 to the x. Okay, this just gives us a basic idea of what's happening. The overall shape of what I'm doing will remain. The specific x and y values would not necessarily remain if I changed the base of 1/2. So let's say we have our x value, of 1. And so if I do an x value of 1, this will clearly give me a y value of 1/2. So something like this. And if I do an x value of -1, this would be 1/2 to the -1, which would then flip the fraction. So this would actually end up being a 2. Sorry about that. 2. There we go. So over here I would have this one. Again, we are getting ever increasingly closer to the x-axis on the right-hand side this time. And on the left-hand side we are sort of shooting upwards. And if you compare these two graphs, they do in fact look like they are reflections over the line y equals, or across the y-axis on the line x equals 0. And if you think about it, that kind of makes sense because this equation right here is actually the same thing as 2 to the -1, and -1 times x would be 2 to the -x. So if you were to compare 2 to the -x to 2 to the x, you'll notice the only difference is that the sign has a negative on the exponent. And when you have a negative sign on your exponent, it does in fact rotate around the y-axis. Now the horizontal asymptote for this one, also y equals 0. And the y-intercept, of course, is still also 0, 1. So we're going to do some examples now. And our examples are going to involve some shifting, translations, reflections, things like that. So starting as we remember, this one here at the end shifts it up 1. And the negative here in the middle is going to be a reflection over the y-axis. Just kind of like we talked about in the last slide. So let's take this graph that we've done and we're going to shift everything up 1. So previously our horizontal asymptote had been at the value 0, right? Y equals 0. Now our horizontal asymptote is at y equal 1. Previously our our y-intercept, had been at 1, and so now it will be at 2. And if I'm taking the standard graph of 3 to the x and then I'm rotating it over the over the y-axis, the graph will look something like this, roughly speaking. Notice my horizontal asymptote got shifted up 1, so now it's at y equal 1. My y-intercept got shifted up 1, so now it's at 0, 2. The domain is still -infinity to infinity, or again any x value is allowed, but my range actually shifted up, so it's 1 to infinity because of the asymptote being shifted as well. All right, very similar example for number 5. You'll notice that same type of a change at the end. This one will actually shift it down 4. And then on the inside, this time we have a -1. If you'll remember, grouping on the inside shifts things left and right, and it happens opposite of what we would expect. So this is a -1, which actually will shift it right 1. Okay, so let's go back down over here and think about what happens. Original graph has a a horizontal asymptote at the y-axis, and we're going to shift that down 4. So if I move that down 4, I've got 1, 2, 3, and 4. So instead of being on the y-axis, I'm going to be right here with my horizontal asymptote. There we go. And then, so this is y equal -4. And then instead of having a y-intercept that would be at 0, 1, that's shifted down 4, which would be at 0, -3. But then the whole graph is also shifted to the right 1. So that point, if you will, it's not an intercept anymore, but that point that was previously right here shifts down 4 and right 1. So we end up at the value 1, -3. And the basic graph of this didn't flip or anything on that one, this one either. And so since the basic graph didn't flip, we're going to sketch our curve in here just like this, getting close to the y-axis or the horizontal asymptote on the left and shooting upward on the right. Again, the overall look is what we're going for. Now, that unfortunately doesn't really answer our question of what is, like the y-intercept. We're going to have to do a little bit more work on this one to find that. Horizontal asymptote is not bad. That one's simply going to be the asymptote that we just plotted, which was y equal -4. The y-intercept is letting x equals 0, right? So if x is equal to 0, I have y equals 3 to the -1, because it's 0 minus 1, and then -4. Well, that's 1/3 minus 4. And if we simplify this, we are going to get, here we go, -3 and 2/3 if you prefer, or even better yet would be -11/3. So my y-intercept is at x equals 0, -11/3 over 3. All right, my domain is still all real numbers, right? It's -infinity to infinity. That doesn't change. However, the range does. The range got shifted down 4, so the range is actually from -4 to infinity. All right, shifting gears a little bit, we're going to talk about solving equations, and then we're going to actually do an application of this material so you can see where it is used, even for most of you, probably in your everyday lives right now. So first of all, equations, exponential equations. In this section, and we will have some different methods we will play with later, but in this section, every time you're asked to solve these problems, you're always going to be able to get the same base on either side. So for example, on the first one, the base is clearly a 2, and it doesn't even look like this one over here is an exponent, right? However, you do see a 2 in it in the denominator. So for starters, we might recognize that both sides are negative, so I can make them positive and or ignore the negatives if you prefer. And what we're going to do is we're going to rewrite 1/2 as 2 to a power. And it is, in fact, 2 to the -1. And then what we're doing is we're noticing that since the bases are the same, I can compare exponents. If the bases are the same, the exponents must also be the same. So this value would actually be x equals -1. Number 7 might be a little bit more difficult to notice it right away. Clearly the right-hand side is 2 to the 1, as it's just written as 2. But the left-hand side also can be written as 2 to the power. In particular, 8 is the same as 2 cubed. So this is 2 cubed raised to the power x. And that allows us to use our properties of exponents to multiply the two exponents together. That's 3x. And I've got 2 to the 1. So now I need to compare these two. Again, if the bases are equal, the exponents will be as well. So this is 3x equals 1, or x is 1/3. All right, let's take a look at an application, super important application. You use it all the time, whether you're realizing it or not. This is an application for interest, in particular compounded interest. We did simple interest before, and now we're going to do compounded interest in this section. A little bit to notice. The equation is a equals p times 1 plus r over n to the nt. One common mistake I'll caution you about as we're solving these is making parenthesis issues and what order of operations happens, because that nt as an exponent needs to be multiplied together before it's the exponent on the 1 plus r over n. So the principle of a situation is either the amount you've loaned or borrowed, loaned/borrowed, or deposited into a bank. Most of the time we see it written as a deposit, but it could be actually done as a loan. T is the length of the investment or loan in years. That's really important that it's in years. R is the annual interest rate, and you must write it in as a decimal, not as a percent. And then A is the amount that you end up having after T years. There's one other type of compounding. It's called continuously compounded. Its equation is A equal P e to the RT. So you notice the P is in there just like on the other ones. The R and the T also like that other equation. The primary difference is that there's a base of E. And the base of E is actually worth approximately 2.718. And we've got a few examples of this one next before we conclude it for today. So it says, suppose you invest $80,000 at 4% annual percentage rate for 20 years. Find the value of the account if the interest is compounded, and then we have different compoundings. So there are some components that are going to be the same. Let me actually write down both equations on the screen. We've got one of them here. I also won't write both of them. There's one of them. The other one looks like this. Okay. So thinking about it and looking at it like that, my principal, the amount that I'm investing, is $80,000. It's 1 plus R over N. R is the rate, and the rate is at 4%. As a decimal, that would be 0.04. And then it's annually, so we'll divide by 1 for one time a year, which also means that I have 1 times 20 for my exponent out here. Although I want to be really careful that I multiply the 1 times 20 or whatever numbers I have before I make them the exponent. If you simplify this, and I'm happy for you to use your calculator to do so, you will find out, including the dollar sign, please, this is money, that you have $175,289.85. Now we're going to do something very similar, of course, for quarterly. Most of the pieces even stay the same. I still have my 80,000. I still have 1 plus the R values, 0.04. And then I have my N value, and this is quarterly, so that means 4 times a year, just like 4 quarters in a dollar, raised to the power of 4 times 20. Now again, as you're putting this in the calculator, in my best recommendation to you, it would be that you actually take and think, what is 4 times 20? Well, it's just 80, and then you use that as you enter it into the calculator. The quantity that we get for this one is 177,337.22. All right, let's try what happens monthly. So A equals 80,000 times 1 plus my R for my interest rate was 0.04. This is monthly, so that means 12 times a year. So this is 12 times 20. And again, I would multiply these first before I continue through the process so that I would actually get, let's see, 240. But that aside, if we simplify properly, we will end up getting that the amount we have after that amount of time is actually 177,806. There we go. All right, also we can look at compounded daily, much the same again. I have 80,000 over here, times 1 plus, my interest rate is 0.04. And I'm going to raise this to, or divide by a daily value of 12, and raise this to the 12t. Oops, sorry, not 12t, 12 times 20. Okay, there we go. Plug this in, simplify, you get 178,035.47. Okay, last one, continuously compounded. This one's a different formula. This is A equals P e to the RT. Principal's still 80,000. E is a number that your calculator will handle just fine. You can use the E in the calculator. And then your interest rate is 4%, 0.04, times the time length, which is 20. And again, I'd multiply the 0.04 and the 20 before I ever used it as an exponent. And if done properly, you'll find out that you have 178,000 $1,043.27.